Hi, so it's my pleasure to introduce David Loeffler from Warwick and Sarah Zerbes from ETHZ. They will be talking on Euler systems and the Bloch-Kato conjecture for automorphic Galois representations. And they are actually here, in some sense of here, and they actually watch them. So it will be a recording, but you are doubly encouraged to ask on Discord because they will actually be able to see your questions in real time and they will be following. So, and hopefully they will answer everything. So I give the floor over to them.
Well, thank you very much for coming to this talk. We'll be starting the recording in a second, as Harold said, but I'll be here live for a short period once the recording is over and happy to answer questions. So please do post any questions you might have in Discord.
So thank you very much for the invitation to give a talk at the ICM. It is a very great honor. So this is a talk jointly with David Loeffler from the University of Warwick. And the title of the talk is Euler Systems and the Bloch-Kato Conjecture for Automorphic Galois Representations. So I want to speak on some recent progress on generalizations of the Birch-Swinnerton conjecture and on the Bloch-Kato conjecture. So let me start by reminding you about the statement of the Birch-Swinnerton conjecture. So I will let E over Q be an elliptic curve. So it is then well known, thanks to the celebrated theorem of Mordell, that if we look at the set of rational points on the elliptic curve, that it has the structure of a finitely generated abelian group. So it is isomorphic to the direct product of a finite abelian group, the torsion subgroup of the elliptic curve, and a number of copies of the integers. And this number of copies is a very important invariant of the elliptic curve, and it is called the rank. Now, attached to the elliptic curve, we have the so-called Hathaway L-function. So it is a complex analytic function which is built up from local data. And the Birch-Swinnerton conjecture predicts that even though the L function is built up from local data, it contains information about the global arithmetic of the elliptic curve. So more precisely, it says that if we look at the order of vanishing at the point s equals 1 of the L function, then this determines the rank of the elliptic curve. And this order of vanishing has a name. It is called the analytic rank of the elliptic curve. And there is a more refined form of the conjecture. Namely, if we expand the L function as a Taylor series around the point s equals 1, then there is an explicit formula for the leading term in terms of the arithmetic invariance of the elliptic curve. And one of these arithmetic invariants is the order of a very mysterious object, namely the so-called Tate-Shafarevich group of the elliptic curve. So this is a very famous conjecture. It's one of the Millennium Prize problems, and it is generally still open, even though some partial results are known. So the first big result in this direction is due to Coates and Wiles, which was proved in 1977. So, which proves the conjecture when the elliptic curve has analytic rank 0. So in other words, if the value of the L function does not vanish at the point s equals 1, and when the elliptic curve has complex multiplication. So the next big step forward is due to Victor Kolyvagin in 1989, who proved the rank part of the conjecture when the analytic rank is 0 or 1, and under the assumption that E be modular. In 2004, Kato gave a new proof of Kolyvagin's result in analytic rank 0. I'm going to say a few more words about the main ideas of his proof later. And in 2014, Bertolini, Damon, and Roger proved some cases of what we call the equivariant Birch-Swinnerton conjecture, where equivariant means that we allow twists of the elliptic curves by artin representations. So they proved the equivariant Birch-Swinnerton Dyer conjecture in analytic rank 0 when E is twisted by a two-dimensional odd artin representations. So we see that some cases of the BSD conjecture are known when the rank is 0 or 1, but nothing is known when the rank of the elliptic curve is at least 2. So nowadays, I mean, the Birch-Swinnerton Dyer conjecture is just the first instance of a vast network of conjectures. So there are many generalizations. So for example, one can replace the elliptic curve by an abelian variety over Q, or one can formulate a version of the conjecture for elliptic curves, or more generally for abelian varieties defined over number fields. And the most far-reaching generalization is the Bloch-Kato conjecture, where the elliptic curve is replaced by a p-adic Galois representation. So let me say a few more words about this. So we let V be a p-adic representation of the absolute Galois group of Q. So V is a finite dimensional QP vector space with a continuous action of the Galois group. So such p-adic representations arise very naturally in number theory. So for example, if we look at an elliptic curve defined over Q, then the p-adic Tate module of the elliptic curve is an example of such a p-adic representation. So to such a p-adic representation, one can attach an L function, which is defined as an infinite product of local terms, and the L function converges when the real part of S is sufficiently large. And the L function is conjectured to have meromorphic continuation to all of the complex plane. So in the case for the Birch-Swinnerton Dyer conjecture for an elliptic curve relates the order of vanishing of the L function at the point S equals 1 to the group of rational points on the elliptic curve. So for a general p-adic representation, we replace the group of rational points by what we call the Selmer group, which is a subgroup of the first Galois cohomology group of V cut out by local conditions. So one can show that it is a finite dimensional QP vector space. And in the case of the Galois representation arising from an elliptic curve, one can show that the group of rational points tensored with QP injects into the Selmer group of V. And one knows that the co-kernel is bounded in terms of the Tate-Shafarevich group of the elliptic curve. So the Bloch-Kato conjecture now relates the dimension of the Selmer group to the order of vanishing of the L function of the dual representation at the point S equals 1. So more precisely, it says that this order of vanishing should be equal to the dimension of the Selmer group minus an error term, namely the dimension of the subspace of fixed points of the representation under the action of the absolute Galois group. And one can show that usually this error term is actually 0. So when V arises as the p-adic Tate module of an elliptic curve, then we nearly recover the Birch-Swinnerton Dyer conjecture. Namely, in this case, the L function of the dual representation is equal to the L function of the elliptic curve. And in this case, the Bloch-Kato conjecture predicts that the order of vanishing of the L function of E at the point S equals 1 is equal to the rank of the elliptic curve plus the ZP co-rank of the Tate-Shafarevich group of the elliptic curve. And if we assume, as is conjectured, that SHA of E is finite, then we recover precisely the rank part of the Birch-Swinnerton Dyer conjecture. So it is almost the same as the Birch-Swinnerton Dyer conjecture when V arises from an elliptic curve. So I now want to go back, to Kato's proof of the Birch-Swinnerton Dyer conjecture in the case of analytic rank 0. So what are the main steps? So the first step is to construct an Euler system for the periodic representation attached to the elliptic curve. So what is an Euler system? It is a collection of cohomology classes in the Galois cohomology of the abelian extensions of Q. So this collection is indexed by the positive integers, and the class Zn lies in the H1 of Q adjoins the nth roots of unity with values in V. One can compare classes for different values of n using the so-called Galois co-restriction maps. And one assumes that these classes satisfy certain compatibility relations as n varies, namely that they satisfy the so-called Euler system norm relations. And these norm relations are closely related to the local factors which appear in the definition of the L function of the elliptic curve. So one should think of an Euler system as a kind of cohomological incarnation of the L function of an elliptic curve. So such Euler systems are very useful because there is a tool called the Euler system machine, which was developed by Kato and Rubin, which says that if V satisfies a large image assumption, and if the bottom class of the Euler system is non-zero, then the Selmer group of V is equal to 0. So in other words, an Euler system is a very powerful tool for controlling the size of a Selmer group. Of course, one now needs a condition or a criterion for checking whether or not the bottom class of the Euler system is non-zero. So the third step in Kato's strategy was to prove a so-called explicit reciprocity law, which relates the bottom class of the Euler system to the value of the L function at the point s equals 1. So in other words, if L of E1 is not equal to 0, then the bottom class of the Euler system is non-zero. And then one can use the Euler system machine to deduce that the Selmer group is equal to 0, and hence proving the Bloch-Kato conjecture and hence the Birch-Swinnerton conjecture in this case. So how does Kato construct the Euler system and prove the explicit reciprocity law? Well, an essential ingredient is to use that the elliptic curve is modular, which is a famous result of Wiles, Taylor-Wiles, and Breuil, Conrad, Diamond, and Taylor. So E being modular means that the periodic representation attached to the elliptic curve corresponds to the periodic representation attached to a modular form, or more precisely, its dual. So here the modular form is of weight 2. And if one knows that E is modular, then this implies that the periodic representation attached to E is a direct summand of the H1 étale of a modular curve base changed to Q bar. And this means that Kato could use the geometry of a modular curve to construct the Euler system and to prove the explicit reciprocity law. So this is the main tool in his approach to proving these new cases of the Birch-Swinnerton conjecture. So the topic of my talk is to discuss a generalization of Kato's results where the elliptic curve is replaced by an abelian surface over Q. So such abelian surfaces arise very naturally. So for example, if one considers a restriction of scalars from K to Q, where E is an elliptic curve defined over an imaginary quadratic number field. So this gives rise to an abelian surface. And one can show that in this case, the Birch-Swinnerton conjecture for the elliptic curve over K is equivalent to the Birch-Swinnerton conjecture for the associated abelian surface defined over the rational numbers. So we want to try and adapt Kato's strategy to this case. Now, as I said, one of the crucial ingredients in Kato's approach is to use that elliptic curves over the rational numbers are modular. So it turns out that at least conjecturally, this should also be true for abelian surfaces defined over the rational numbers. Namely, the paramodular conjecture predicts that there should be a correspondence between, on the one side, abelian surfaces over Q, where the ring of endomorphisms of A is equal to Z, and certain genus 2 Siegel modular forms of parallel weight 2 on the other side. And this correspondence attaches to the p-adic representation of an abelian surface, the dual of the so-called spin representation of a certain genus 2 Siegel modular form. So what is a genus 2 Siegel modular form? It is an analog of a modular form for the symplectic group GSP4. And these correspond to global sections of certain line or vector bundles on Siegel threefolds. So some instances of this paramodular conjecture are known. So Berger and Klosin proved it when the genus 2 Siegel modular form is congruent to a Saito-Kurokawa lift. So Boxer, Caligari, G, and Piloni proved potential modularity. And there are some very recent results by Alan Curry and Thorne and by Karayani Newton, who proved very general results about the paramodular conjecture for the case when the abelian surface arises from an elliptic curve defined over an imaginary quadratic field. So this looks very promising, because if one assumes this conjecture, we can attach to an abelian surface an automorphic object, namely a certain genus 2 Siegel modular form. Now the problem is that even if we assume that the abelian surface is modular, the p-adic representation is not a direct summand of an étale cohomology group of a Siegel threefold base change to Q bar. So this is problematic, because the hope is that one could use the geometry of a Siegel threefold to construct an Euler system for the p-adic representation of an abelian surface. However, something weaker is true. Namely, if A is modular, and we assume that it is ordinary or small slope at a prime P, then the p-adic representation attached to the abelian surface is the p-adic limit of the dual of the spin representation of genus 2 Siegel modular form of weight K1, K2, where K1 and K2 are both at least 3. And these genus 2 Siegel modular forms, so where the weight, satisfies this condition, are called Siegel modular forms of cohomological weights, because in this range of weights, this dual of the spin representation does actually occur in the H3 étale of a Siegel threefold base changed to Q bar. So in other words, while Vp of A does not directly appear in étale cohomology, it is the p-adic limit of representations which do. And this is not a new phenomenon. One sees something very similar for the p-adic representation attached to weight 1 modular forms. They do not themselves appear in the étale cohomology of a modular curve, but they arise as a direct limit of p-adic representations attached to modular forms of higher weight, which do appear in the étale cohomology of a modular curve. So this suggests the following strategy for constructing an Euler system for the p-adic representation attached to an abelian surface. So the first step, which David Loeffler and I carried out together with Chris Skinner in 2016, was to construct an Euler system for this dual of the spin representation of a genus 2 Siegel modular form of cohomological weight. And because this representation arises in the étale cohomology of a Siegel threefold, we can construct this Euler system using the geometry of the Siegel threefold. And once one has this for genus 2 Siegel modular forms of cohomological weight, so one can show that these Euler systems interpolate in p-adic families. More precisely, one has a 3-parameter space, namely one has 2 weight variables and 1 variable which takes care of the cyclotomic twists. So, I mean, this result was proven by David and myself together with Rob Rockwood last year. And then, I mean, by specializing this family in parallel weight 2 for a suitable cyclotomic twist, we obtain an Euler system for the p-adic representation attached to an abelian surface. So how do we construct this Euler system for a genus 2 Siegel modular form of cohomological weight? Well, so we consider an embedding of the product of 2 modular curves into a Siegel threefold. I mean, this embedding can be very easily seen, I mean, on the level of groups. I mean, someone constructs an embedding from the fiber product of GL2 with itself into GSP4. So such an embedding gives rise to a push-forward map in motivic cohomology. So more precisely, from the H2 motivic of y squared, so where y is a modular curve, into the H4 motivic of a Siegel threefold. And we can then compose this, I mean, first with the étale regulator into p-adic étale cohomology of the Siegel threefold. And then, I mean, via localization, the Hochschild spectral sequence, and using the fact that the p-adic representation attached to F, I mean, arises in the étale cohomology of the Siegel threefold base change to Q bar, we can map it into the H1Q of the p-adic representation that we are interested in. And the idea for constructing the bottom class of the Euler system is to take suitable elements in the H2 motivic of y squared and define the bottom class of the Euler system to be the image of the suitable element under the sequence of maps. So in the element that we consider in the H2 motivic of y squared is the exterior cup product of 2 motivic Eisenstein classes attached to GL2. So these motivic Eisenstein classes should be thought of as cohomological incarnations of GL2 Eisenstein series. So in parallel weight 3, they are just the classical Siegel units. So this is the construction of the bottom class of the Euler system. So to get classes defined over the cyclotomic extensions, one has to twist the embedding slightly. And of course, it is then a very big challenge, I mean, to prove the norm relations. And we showed in our paper with Skinner that this question can be answered using smooth representation theory. Now, we have just constructed an Euler system for the p-adic representation attached to an abelian surface. But the problem is that we need a criterion depending on the L value to check whether the bottom class of the Euler system is non-zero. So in other words, we need an explicit reciprocity law which relates the bottom class of the Euler system to the value of the L function of A at the point s equals 1. So the idea is, firstly, to prove such a relation for the Euler system attached to a genus 2 Siegel modular form of cohomological weight. I mean, this seems like a sensible first step. I mean, because there we actually construct the Euler system using geometric methods. And then to use a p-adic limiting process, which more precisely is variation over the GSP4 eigenvariety, to deduce the explicit reciprocity law that we want. So in order for this to make sense, we need to replace the spin L function of a genus 2 Siegel modular form by what is called a p-adic L function, which is a p-adic analytic function interpolating certain so-called critical values of the spin L function. I mean, we need to do this because otherwise we can't use a p-adic limiting process, because the L values per se, the complex L values, do not vary in p-adic families. So this means that we are faced with two problems. So firstly, we need to construct a p-adic L function, say, which interpolates the critical values of the complex L function. And we need then to prove a relation in cohomological ways between this p-adic L function and the bottom class of the Euler system. So let me make a remark here. So there already exists such a p-adic L function with the right interpolation properties, which was constructed by Dimitrov, Januszewski, and Dragoram in 2018. However, it uses transfer from GSP4 to GL4. And this is not in the least bit related to the construction of our Euler system. So there is very little hope, I mean, of using their construction and to relate it to the Euler system construction. So what we really want is a construction of a spin p-adic L function, which is related to the Euler system construction. So in other words, which uses the same ingredients that we used in the construction of the Euler system. So what were those ingredients? Well, we used the embedding of the product of a modular curve with itself into a Siegel threefold. And we then considered the push forward along this map, and we pushed forward two GL2 Eisenstein classes. So this suggests that a good starting place for constructing a spin p-adic L function is the Piatetsky-Shapiro integral formula. So this integral formula expresses the critical values of the spin L function, so up to an explicit non-zero factor. So as the integral over y squared of the exterior cup product of two GL2 Eisenstein series, so with the pullback of a certain differential attached to our genus to Siegel modular form under the embedding iota. So I mean, this integral formula clearly is built up from the same ingredients as our Euler system class is built up. So I'd like to make a note here, namely that this differential is neither holomorphic nor anti-holomorphic. So now in 2004, Harris gave an algebraic interpretation of the Piatetsky-Shapiro integral formula. Namely, he showed that one can write it as a cup product pairing in coherent cohomology. So the idea for the construction of a p-adic L function is now clear, namely to interpolate this cup product pairing in coherent cohomology p-adically. And this is where the problem lies, namely the coherent cohomology class, which corresponds to this differential form eta f, does not lie in the lowest or the highest degree coherent cohomology of the Siegel threefold, but in one of the intermediate degrees. And classical Hida theory does not apply in this case. So we did not know whether this coherent cohomology class attached to the genus to Siegel modular form varies in p-adic families. But in 2017, Vincent Piloni developed a new theory called higher Hida theory, which proves precisely that higher coherent cohomology of Shimura varieties interpolates in p-adic families. And this was really the key to the construction of a p-adic L function. So we completed this construction in 2019 in joint work with Piloni and Skinner. So more precisely, we proved the following result. So let A over Q be a modular abelian surface and assume that A is ordinary at P. So in other words, A gives rise to a point PA on the GSP4 eigenvariety. And we assume that the genus 2 Siegel-modular form attached to A is deformable. So deformable is a condition which is slightly weaker than etalness of the GSP4 eigenvariety in a neighborhood of the point PA. And we also assume that there exists an odd Dirichlet character chi, such that L of A times chi at the point S equals 1 is not equal to 0. So this condition has to do with the precise interpolation properties of the Piasecki-Shapiro integral formula. One can show that then there exists an affinoid U containing the point PA and a function defined over U times weight space with the following properties. Firstly, if we take this function and we evaluate it at the point PA corresponding to the abelian surface and at the point S equals 1, then up to an explicit non-zero factor, we obtain the value of the complex L function of A at S equals 1 divided by some period. And if we specialize it at a point in U which corresponds to a classical form FQ, which is of cohomological weight, then the function LP spin of QS interpolates the critical values of the spin L function of FQS. So in other words, we have constructed a 3-parameter p-adic L function. Yeah, and as I said, the deformability condition, slightly weaker than etalness, it describes the geometry of the eigenvariety around the point PA. So once we had this p-adic L function based on the Piasecki-Shapiro integral formula, we could ask the question, how does it relate to the Euler system? So in 2020, David and I proved the following result. So first in cohomological weight. So suppose that we take a point in our affinoid U, which corresponds to a classical genus 2 Siegel-modular form FQ of cohomological weight, then the bottom Euler system class attached to FQ corresponds or can be related to non-critical value of the spin p-adic L function specialized at FQ. So this is a non-critical value, so it does not correspond to a complex value of the L function. However, one can deduce from work of parallel U that this relation that we proved deforms in p-adic families. So we have now on the one hand an Euler system, which we know deforms in p-adic families. By construction, the p-adic L function deforms in p-adic families. And we have this relation which equally deforms in p-adic families. And this means that we can twist the Euler system or deform the Euler system p-adically until we reach critical values. And this leads to a proof of the Bloch-Kato conjecture in analytic rank 0 for the critical twists of the dual of the spin L function of the Siegel-modular form FQ in cohomological weight. But of course, we can also specialize to parallel weight 2 and a suitable cyclotomic twist to establish a relation that we want, namely a relation between the bottom class of the Euler system attached to the abelian surface and the value of the L function of A at the point S equals 1. So now that we have that, we can feed it into the Euler system machine and deduce applications to the Birch-Swinnerton Dyer conjecture. So last year, we proved the following result. So let A over Q be an abelian surface and assume that it is either generic or that A arises from an elliptic curve defined over an imaginary quadratic field. And we assume that the elliptic curve does not have complex multiplication. So we assume that the abelian surface is modular. We also assume that there exists an odd Dirichlet character chi, such that the product of L of A1 and of L of A times chi1 is not equal to 0. So we choose a prime P such that A is ordinary at P, and that the genus 2 Siegel modular form attached to A is deformable in the sense that I explained above. And we also assume that the representation VP of A has big image. So this is needed for the Euler system machine. Then the group of rational points on the abelian surface is finite, and the P part of the Tate-Shafarevich group of A over Q is finite. So in other words, the rank part of the Birch-Swinnerton Dyer conjecture holds. So this is an analog of the result that Kato proved for elliptic curves defined over Q. So in the case when the elliptic curve arises, when the abelian surface arises from an elliptic curve defined over an imaginary quadratic field, and if the analytic rank of the elliptic curve is not equal to 0, the existence of a suitable character chi is automatic, because we can just take chi to be the character attached to the imaginary quadratic field, which does not change the value of the L function. So in this case, assuming that L of E1 is not equal to 0, we deduce that the rank of the elliptic curve is 0, and that the P part of the Tate-Shafarevich group of E over K is finite. So let me also say that we obtain analogous result for the equivariant Birch-Swinnerton Dyer conjecture, namely for an abelian surface twisted by a two-dimensional Oort-Artin representation. So in this case, we do not work with the Euler system attached to automorphic representations of GSP4, but to automorphic representations of GSP4 times GL2, which was constructed by Xu Jin and Sakamoto. And it turns out that for this, that proving the explicit reciprocity law for this Euler system is completely analogous to the proof that I just explained. So we then obtain some results on the equivariant Birch-Swinnerton Dyer conjecture for an abelian surface twisted by two-dimensional Oort-Artin representations. So to finish, let me just say, with the methods that David Loeffler and I introduced, we have constructed many other new Euler systems. So for example, for the Assay representations attached to quadratic Hilbert modular forms, and for the representations arising from the unitary group GU to 1. And we believe, or we are confident, that the methods that we introduced here to proving explicit reciprocity laws using hierarchy theory, that these will apply in these cases as well. So that should lead to many new cases of the Bloch-Kato conjecture for automorphic Galois representations in analytic rank 0 in quite wide generality. So thank you very much for listening.
Hello again.
Well, thank you very much for the wonderful talk. And I think Sarah will materialize.
I think she may have left her camera off, but I'm here to represent the two of us. And we had set aside this little bit of time at the end for questions. So if anyone in the audience, if you have questions and you'd like to ask them now, please do feel free to post them on the Discord server. And if you don't have time to post them now, we will be checking back over the next few days and answering questions offline. And those of you who are coming to the in-person event that Sarah and I are organizing next week at ETH Zurich, we can also ask questions then. And just while we're waiting to see if any questions appear, I want to make just a brief remark, something which we meant to put in the talk, but which got accidentally left out, which is that the results that Sarah mentioned on explicit reciprocity laws for GSP4, there is a geometric statement about rigid cohomology of Siegel-Shimura varieties, which is necessary input for this work. And the version of the proofs that is currently written up and available on the archive actually assumes this and refers to forthcoming work of Lan and Skinner. So Kai-Wen Lan has informed us that he has that he is working on this and expects to have a proof ready very shortly. So the results will be rendered unconditional very soon, we hope. So at the moment, that one ingredient has not yet been released publicly, but we hope to have it before very long.
Very good.
I'm not sure if there are any questions appearing in Discord. I haven't seen any.
Yeah, I haven't seen any either.
Okay, perhaps we should wait for a moment just to see if any questions do get asked. But, I'll use the time to once again thank the organizers of the International Mathematical Union for this fantastic opportunity to speak in this conference. So thank you very much for this opportunity. It's wonderful to be able to participate.
Well, let's thank the speakers again. I'm feeling deeply stupid because I don't have any questions, but excellent. I will be looking at Discord and see what they say, how they answer the questions that I'm sure some people will have.
Well, thank you. Perhaps we should stop there in that case.